Our second speaker this morning with Federico Ardila intersection theory of Matroids, variation of English.
Okay, first of all, thank you so much, Paolo, Dave, Juni, Leonardo for organizing this conference, and Juni, I think you put in a lot of work this year in order to let a lot of us have a lot of fun talking about mathematics, and it's been a really great joy, so thank you for that. My goal for today is to tell you about a very nice productive conversation between intersection theory and Matroids. I'm going to be talking about the work of many people. All my work that I will be talking about today is joined with a number of people. Carly Clivens, Alex Flink and Felipe Rincon, Graham Denham and Juni Hall, Chris Ira and Raul Penaguiao, and Graham Denham and Chris Ure and Juni Hall. And the summary is just that intersection theory and combinatorics. I mean, I feel like I'm preaching to the choir here, but intersection theory and combinatorics really have a very rich, beautiful interaction that, in fact, benefits both the intersection theory and the combinatorics. Okay, let me start with motivation that I think you'll be familiar with, which is the question of coloring maps, right? So you have a map, you have P colors, and you want to color each state in a color so that two neighbors are never have the same color. Guthrie had the conjecture that this could always be done with 4 colors, and this was open for over a century. And Birkhoff had the idea that maybe what we could do is say, okay, maybe instead of just proving that this can be done with 4 colors, why don't we say, let's say that there's T colors and find how many colorings there are. Okay? And it's not hard to prove that this is a polynomial in T called the chromatic polynomial. Again, I think maybe most of you are familiar with this, but I'm not sure if all of you have ever seen a large chromatic polynomial, and I realized that I had never seen one. And that's what lock-in cavity looks like, it turns out. This I felt very excited about, because how long is a number is the logarithm. And so this says that the logarithms are concave. So this was I actually don't know what the original motivation to make this conjecture was, but I think, you know, the idea that Birkhoff wanted to say, okay, we just have to prove that 4 is not a root of this polynomial, right? If this polynomial is evaluated at 4 is not 0, then it must be positive, so there is a coloring. And then this places into the realm of algebra, but also of locating roots of polynomials, lock-in cavity, and so Welsh and Rhoda conjectured that this polynomial is lock-concave, both in the case of graphs and in the more general case of the characteristic polynomial of Matroid. And this was proven by Juni Hall in 2011 for graphs, by Karima Di Pasito, Juni Hall, and Eric Katz for Matroids. The sequence is lock-concave. And as you may be aware, intersection theory played a very central role in this, because as combinatorialists, when a combinatorialist sees a number, we often ask, okay, what does that number count? The kind of combinatorialist that I am, you often try to find, okay, what does it count either algebraically or geometrically or topologically? And in this case, the key insight was the answer to the question, what do these numbers count geometrically? And the answer is intersection theoretic. So that's one combinatorial motivation. One geometric motivation for the story that I'm telling today starts a long time ago, and maybe a very early result by Bezout from the 1700s is that if you take 2 general curves in the plane of degree m and n, then they're going to have generically n times n intersection points. So this intersecting 9 points, a quartic and a quadratic intersecting 8 points. And so these are the kinds of intersection theoretic combinatorial computations that you want to try to be able to do. So more generally, you can ask, okay, let's say that you have some ambient variety and you have some subvarieties inside of it, and you want to know how do the subvarieties intersect with each other. Okay. And intersection theory is the answer to this question, and you should do this carefully. For example, you need to count multiplicities correctly. This we know since high school, that sometimes roots counts as double, and so on. It's also important that the answers behave well with respect to rational equivalence of subvarieties. So, for example, in order to say cubic intersection cubic, you need to answers to behave well under those equivalences. And Chow constructed this ring, the Chow cohomology ring, that organizes these computations. Okay. And so the key question that I'm interested in today is how do you actually compute in a ring like this? How do you compute in these Chow rings combinatorial? Now, as you can imagine, in general, these Chow rings are really complicated. They tell you how, inside a variety, all the subvarieties intersect. So in general, you wouldn't expect this to be a very computable ring. Today I'm going to be focusing on a very rich, very beautiful special case, which is the case of Toric varieties. So when the ambient variety is a Toric variety corresponding to some rational polyhedral fan sigma, then it turns out that as often happens in these kinds of things, the Chow ring of the Toric variety can be described completely in terms of the fan. Okay, and so that means that all of a sudden it becomes much more amenable to combinatorial techniques. And an important example that I will be talking about today, and I actually drew it here because it will be useful to look at it, is the example of the Bermuda fan, or the braid fan. So here what I have is I am in Rn mod R. I'm looking at the hyperplanes xi equals xj. I guess I call them ti equals tj here. In order to determine a region of the arrangement, you have to decide which side of each hyperplane am I on? So is ti bigger or smaller than tj? So therefore, in order to decide which region you're in, you need to decide what is the linear ordering of the variables. So the chambers are in bijection with the permutations of 1 up to n. Okay. So this is the braid fan, the permutahedral fan. And a lot of the story that I'm talking about today takes place in the permutahedral variety, which is the Toric variety corresponding to this fan, which is also in the study of modular spaces of curves. This is also called the Los-Hermanian space. So let's talk about this permutahedral fan in a little bit more detail. So I already talked about why the facets, the full dimensional regions, correspond to permutations. Now, if you go to the other extreme, to what are the rays, then if you compute them carefully, you find that the rays correspond exactly to all the 0, 1 vectors, except for the all zeros vector and the all 1 vector. So you have a ray for each, and that's what I'm calling E sub S, the indicator vector of the subset S. Okay. And then I want to say this slowly because it's going to be very important that in this fan, okay, so I have my 6 rays corresponding to the 6 non-empty proper subsets of 0, 1, 2. And now if I want to know which sets of rays form a phase, the answer is that the corresponding subsets should be a flag. Okay, so 0 is a subset of 0, 1, so that's why these two form a ray, a cone. But for example, these two aren't comparable, so they don't form. So in other words, the cones correspond to the flags. So that's going to be the permutahedral fan, where a lot of this is taking place. So let me tell you about the intersection theory of Toric varieties. So I mentioned that the Chow ring of a Toric variety can be described in a way that depends only on the fan, I'm going to focus on the case of complete simplicial fans. For some of the results, I'm going to say you can have weaker hypotheses, but let's focus on a complete simplicial fan like this one. And so in this case, there are several beautiful descriptions that actually look very, very different from each other. And so what I want to do next is just show you three very different ways of thinking about these rings. Okay, I'm going to spend some time on these three, and I also want to say that there's others that I could talk about. I'm going to discuss them briefly, and then illustrate them carefully with this example. I should have said that I have this survey paper where everything, or almost everything that I'm going to say that is spelled out in careful detail. Okay, so again, you're looking at subvarieties of the toric variety of sigma and how they intersect. And now we're going to find three ways of thinking about it. So the first way is due to Danilov and Brion. They give an algebraic combinatorial presentation in terms of generators and relations. Okay? And this is all very explicit. So what you're going to get is that the generators are going to correspond to the rays of the fan. In this case, the rays of the fan are the subsets, but in general, they're the rays of the fan. Modulo two ideals I and J. This ideal I is the Stanley Reasoner ideal of the fan. In other words, it tells you what are the minimal sets of rays that don't form a face. Okay? So in this case, as I just mentioned, XS and X, the ray S and ray T don't form a cone if they are incomparable. So this is going to be the Stanley Reasoner ideal. In general, you're going to have higher degree terms, but in this case, it's only pairs that are enough. And then you get these linear relations that are paying attention, in essence, to what are the angles of the rays. Okay, so this is kind of the information of the incidence of the rays, and this is the angles of the rays. In this case, they look like this, and in general, there are also these very explicit linear relations. Okay. So in order to compute in this ring, all of a sudden this becomes what I think mostly in Canada people call combinatorial algebra, which I really like, which is that you do algebra with objects that are combinatorially indexed, and then it becomes this fun game of how do you compute algebraically in the presence of combinatorial structure. And I want to give you I'm trying to be very explicit today, so I am going to give you an example for this particular one. Okay, let's just compute this. Compute it. So okay, so in degree 1 I have the constants. In degree 2 I have 6 generators, but these relations for every pair I and J, you have a relation that looks like this. So you're going to find that there's 2 relations, which means that out of the 6 generators, 2 of them cancel out, and these 4 generate the linear thing. And it's not obvious ahead of time, but there's only one thing in degree 2, which is generated by x0, x0, 1. And just to show you what these kinds of computations look like, I want to show you why, for example, x1, x0, 1, which also lives here. This says it should be a multiple of this. So how do I know that? It turns out that x1, x0, 1 is equal to x0, x0, 1. And in order to compute that, this is what I would call combinatorial algebra. Okay, you do this, x0, x0, 1 minus x1, x0, 1. You can factor out the x0, 1, you get x0 minus x1. And then you have this relation that allows you to rewrite x0 minus x1 in this way. And then expand it out. And then you find these are pairwise incomparable, and you get 0. Okay? The details are not super important, but the point that I'm trying to make is that these are the kinds of things that you have to do that are kind of combinatorially structured computations.
Are there actually theorems proved by like looking at computing these presentations very hard and then?
Yes.
What is that?
I will show you. I will show you several. I will show you. Yes, there are theorems that are only known by doing some kind of this.
Thank you.
So this is the first way. I think you like to do this kind of thing.
I do, very much.
Right?
Yes.
And so for us, this is kind of fun, right? And it turns out to be really powerful.
Yes.
For somebody else, maybe this is not your favorite way of doing it, and so you might prefer other ways. And so let me show you a second way, due to Billera, which I find really amazing. And actually, I want to say this is coming from the theory of splines. Billera is one of these people who taught me that there's no difference between pure and applied math. He actually studied applied math in various important ways. And the theory of splines is actually how you build airplanes. So you're trying to build some kind of surface, and you want to kind of cut it up into pieces, and each piece should be given by some polynomial function, and the polynomial functions should agree on where they meet. This is what a spline is. Okay. And the theory of splines really belongs largely to the theory of geometric modeling and numerical analysis. And he realized that it also has something to say in this setting. Okay. And I think it's kind of an amazing result that the Chow ring of the Toric variety of sigma is just the ring of piecewise polynomials supported on that fan, modulo linear functions. Okay. So okay, you have to. So the way that you want to think about this is you have some fan. In this case, you have 6 chambers, and so you have to put a polynomial in each chamber. But these polynomials need to agree where they meet. And at first I found this really hard to think about, but you get used to thinking about how to do something like this. And again, in the interest of being very explicit, I want to show you what these things look like. So you get the constant 1. Okay. Here, for example, you get, I put zeros here except T0 minus T1 and T0 minus T2. Okay. So for this to be well defined, T0, T1, T0 minus T1 and T0 minus T2 better agree on this ray. And they do, because if I did this correctly, T1 is equal to T2. And that's what that plane is. Here, 0 and T01 are supposed to agree on this ray, which means this better be the ray T0 equals T1, and it is. So on. So that lives there. In fact, I'm showing you for the generators x0, x1, x2, and x01, what are the corresponding piecewise linear functions. And then the multiplication is very simple. You just multiply 2 piecewise polynomial things that you get a piecewise polynomial thing. Okay. Let me say one thing about the dictionary, which is that actually the way that you get enough of these is that for each ray, you can consider the function that is 1 at that ray and 0 at all the other rays. So this is called the tent function. And again, this is coming from splines. It's a very natural thing to do in splines. And so that's what these tent functions are. So, and the fact is that they do generate everything. Okay.
So when you say 1, you mean linear increase along that, right?
Yeah. So maybe you pick the first lattice point and you put it, and you have value 1 there, 0 on all the other rays, and then these other functions that I did. So let me show you now what a computation here would look like. So let's do the same computation from the previous slide. x0, x01 minus x1, x01. So you just multiply this times this, minus this times this, and you get this, okay? And I was expecting it to get 0, but this doesn't look like 0. But then I have to realize, actually, this is minus T10, T02, T01, T12. I can actually factor out a T01, and I get this thing, okay? And I actually model it out by linear functions. Linear functions are what I mean is the ideal generated by that. And this is a linear function times something which I should hope lives in the ring. And so to check if it lives in the ring, I have to see if it is continuous on this, and actually this is equal to this one. So that's why this is equal to 0. And these kinds of computations can be really tricky. Sometimes things are 0, but it's not at all obvious that they are 0 until you figure out how to express it as some combination of linear function times something. So multiplying is very easy, but for example, checking that something is 0 is quite tricky. So that's another way of computing in this ring. Okay, the third one is coming from the theory of Minkowski weights. This is due to Fulton and Sturmfels, but I would argue is one of the foundational papers in tropical geometry. I wouldn't just argue, this is just a fact that this is one of the foundational papers in tropical geometry. And what they found is that the Chow ring of the toric variety can be identified with the set of balanced subfans of your fan. And you might prefer just putting the word tropical here. These are with the tropical fans that are supported on SIG. So these are subfans like this one, where you have weights on the facets, and the weights should be balanced at each ridge. So this is of dimension 1. So at every place in dimension 0, when you look around, the forces around you should balance. This plus this is equal to 0. For example, here, this is 2D. So around here, this direction with weight 1 and this direction with weight 1 should balance. Again, I think this takes some getting used to, but tropical fans, there's a lot to be said about them. There's a lot that you can do. And in particular, for the permutohedral fan, these are some tropical fans or balanced fans that generate each other. Question?
So in the middle 4 pictures, the ones are actually on the lines, but in the far right picture, the ones are on the sectors. Is that right?
Yeah, thank you. That's right. I'm just going to repeat what you said. Here, the ones are on the rays. Because these are Minkowski weights of dimension 1. The Minkowski weights of dimension 2, the ones go on the 2D phase. And here it just goes on the 0D phase.
So in the middle, the ridge would be the vertex in the middle, or?
Exactly.
Okay.
But on the right, the ridges are the rays.
Yeah.
Okay. So
You don't have the one with the 6 rays one?
you do, but then it's this plus this plus this. And so that tells me how to add. But one thing that you'll realize is that this is supposed to be a ring, and it's not at all clear how you're supposed to multiply these things. This is what is done by this something called the fan displacement rule, which still seems a little bit magical to me, which is that if you want to multiply two Minkowski weights, what you do is you put them on top of each other, you wiggle one of them a little bit, and then you see what the intersection is, and you unwiggle. And so a couple of amazing things happen. One is that the answer doesn't depend on how you wiggled. And 2, the result is a balanced fan as well. So that's what this is saying. And this is a fun example. Already here. You should try this for things that are not tropical to see that this shouldn't work. But for tropical things, it works. That no matter how you wiggle these two things, they're always going to meet at 2 points. But if you do it with something that's not balanced, that might not happen. There is one thing that I have to say, which is that there can sometimes be some additional weights that arise from the arithmetic of the situation. So whenever you get an intersection point like this, for example, you get a weight that's given by the index of the lattice generated there. So you get like some determinant there that you have to keep. But that's the product. Okay.
Where does the balancing condition come from?
Where does the balancing condition come from?
Rational equivalence.
Rational equivalence. Okay. And I think another thing we're saying is that it ends up being equivalent to the fact that this fan displacement rule is well defined.
So the Billera spline stuff makes a lot of sense for non-toric varieties. If you want the different homology, somebody who's not a toric variety. Does this one generalize to non-toric variety?
For non-toric varieties, I bet that there's people here qualified to answer that question, but I wouldn't be one of them.
I mean, it's seeing how things intersect strata, so I don't know how useful the description would be, but you could probably associate a Minkowski-ish weight to a coma or to a cycle class. But I don't know how much this would capture.
Yeah. Let me add that there's tropical geometry has a lot of techniques to do computations like this. And maybe the other thing that I'll say, Dodgy, is that to answer your question 3 times. So for each one of these 3 methods, there are proofs that actually that there seems to be the simplest method. So, but it's sometimes also a matter of taste of it and expertise if you're trying to do something, which one of these techniques you'll want to do. But, okay. I have to mention this also, that although this is not the kind of main goal of my talk, there's been this whole development of combinatorial Hodge theory that is very much a part of the story. The parts that are most relevant to us, these Chow rings are always graded of degree D. They correspond. They have the Lefschetz package, so you have like Poincare duality, our Lefschetz, Hodge-Riemann relations. Most relevantly for us for this moment, basically the degree D piece is just a copy of the ground field. So it's called the degree map. Everything of degree D you can just think of as a number, like the intersection number. Okay. And under suitable hypotheses, Hodge-Riemann relations hold, and they give you inequalities of this sort. And this is how a lot of log concavity results are proved. And we have talked a lot about this story during this program. I think what I really want to emphasize on is how do you get these numbers, though? So in order for this to give you combinatorial consequences, you really have to be insightful about what are the classes that you want to intersect. Intersect D classes, you get some number. What is that number? So if you choose them insightfully, you get some beautiful intersection theoretic calculations, which it'll give you log concavity conjectures and other kinds of conjectures. But what I really want to focus on is how do you actually compute these things? So let's talk about the intersection theory of matroids. And I think that if you know and love matroids, you know and love matroids. And if you don't know and love matroids, maybe now is not the moment to try to say too much about them. Although I think anybody who knows me knows that I would love to talk to you about matroids for a very long time. But if you're not used to thinking about matroids, feel free to think about a vector configuration or a graph. Okay. So for a vector configuration, I'm looking at what are the bases that I can make using those vectors. This is them. For a graph, I'm looking at what are the spanning trees that I can make, and this is them. That's called the matroid. Okay. And both of these notions satisfy this exchange property. That if I take 2 bases, I can take any element of one of them, I can replace it with an element of the other one. It's something that we often teach in a linear algebra class. And Nakazawa and Whitney basically decided, why don't we call a matroid anything that satisfies these properties? Okay. So it's some kind of capturing what linear algebra graph theory have in common, but it turns out that also algebraic independence, matching theory, routing theory, there's many setups. Okay. Now, to a matroid, I'm going to associate a fan. And the way that I'm going to do it is that I'm going to first consider the lattice of flats, okay, which is easiest to describe in the case of vectors. The flats of this matroid are just the span subspaces, so the lines A, B, C, and D, E. the planes AB, BC, ADE, BCDE, the full thing and the everything. And then I'm going to take that information and encode it in a fan. Okay. What I'm going to do is for each one of these flats, I'm going to look at the corresponding ray. So like ADE is going to become the indicator vector of AD and E. And then I'm going to fill in flats. I'm going to fill in cones whenever I have a chain of flats. So for example, because B is subset of B, C, D, E, that means that I put a cone between ray B and ray B, C, D. This is called the Matroid fan or the Bergman fan. And given that we have the braid arrangement, you can also think, just, here's all the rays. Now look only at the rays that are flats and see what's the induced subfan. That's the Bergman fan. Okay. So we introduced this in 2006 with Carly Clivens because of tropical geometry. So this was very early on in tropical geometry, where we were just like asking, what do tropical things look like? And the question was just, what happens if you take a plane? What happens if you tropicalize it? And the answer is this, that if you take a linear subspace, so you start to the end, so then its tropicalization is going to be exactly the Matroid fan for the Matroid associated to that. Maybe just a small historical note that the way that we got interested in this is because Bernd Sturmfels had he suggested studying the tropicalization of linear subspaces and in general an associated fan for a Matroid, and he wanted to know if this thing was connected, pure and connected, which is something that tropical geometry hopes is true. But we found that the way of proving that was to find that there's more structure here. There's a very nice combinatorial structure. And in fact, the topology follows for free because Bjorn had already studied the topology of this thing. It's a wedge of spheres. So that's why it's pure and connected, but it's also a very combinatorial structure. And in particular, it's a balanced fan. So that's another thing that I should say. When you tropicalize a variety, the result is always balanced. Okay, Matroid fans. What are Matroids really? This is a question that I very often ask myself, and I don't want to spend time with this slide. I just want to put some words in front of you, and if any of the blue things stand out to you and you want to ask me about them later, I'm happy to tell you about this later. Every one of these points of view ends up being important to the story that I'm telling today, but I'm not gonna say much about it. Feel free to ask me about it later. The one thing that is important is that I want to get to this statement that Matroids are the tropical fans of degM. So that's what I want to say next. So Matroids, as I already mentioned, arise in tropical geometry. I won't say too much about tropical geometry except to say that we have let's say a projective variety. You can tropicalize it in this way, and what this does is that it keeps track of the behavior of the variety at infinity. The tropical variety ends up being a piecewise linear object that loses a lot of the information, but it retains the information. It retains some information about the original varieties. If I look at something like this. Okay, here I have a more careful definition of tropical fan or a balanced fan. It should be a pure d-dimensional fan. It has weights on the facets, and around each ridge tau. What you do is that you look at the facets containing it, and then you look at this represents tau is d-minus one dimensional, sigma is d-dimensional, so there's an extra ray to make sigma, and you look at the first lattice point in that ray. So that's like the direction of pulling. This is the weight, the strength that you're pulling with, and it should balance and equal 0. Okay. So this is the definition of a tropical fan. It's a fact that any tropicalization satisfies this. Okay. But it turns out that many tropical fans don't come from tropicalization, and that if you want a robust theory, you want to include them all. Okay. If you're used to thinking about realizable matrix versus all matrix, this is the same thing as tropicalized versus tropical. You have a notion of tropical degree. So just like in the classical case, if you want the tropical degree of something of dimension d, then you intersect with the hyperplanes and see what's the number of intersection points. Here alpha is the tropical hyperplane, so it's the tropicalization of a hyperplane. Okay. And one nice fact is that one of the things that tropicalization preserves is degree. So you can compute degrees before or after tropicalization, you're going to get the same answer. But it turns out that tropical degrees are also interesting by themselves, and that's very much part of the story today. That even if you're not interested in kind of classical algebra geometric degrees, there are some interesting things to be said. And in particular, this theorem from Alex Fink's PhD thesis, I really like, that if you want to know what are the tropical fans of degree 1, they're exactly matroids. So you could define a matroid to be a tropical fan of degree 1. So it's like in the tropical world, what it means to be linear. Okay, so now what I want to do is I want to talk about a computation intersection theory of matroids. So I'm in the permutohedral fan. I already mentioned the matroid fan that is supported here. And you can tropicalize the hyperplane, and you can take the minus that, which is the comonomial transform or the inverse hyperplane. And these are all balanced fans living inside this. They're all Minkowski weights in this Chow ring. And so what I was mentioning about these numbers is that the coefficients of this polynomial are exactly the numbers that you get by intersecting the matroid fan with r minus k powers of alpha and k powers of beta. Okay. And so what I want to do next, very briefly, is to show you what partly what I wanted to do with this project when I wrote this survey is that I actually wanted to just see like what happens when you try to prove this using the different methods. So I want to just show you what does a proof of this statement look in each one of these worlds and what it teaches. I'm not going to go into details, but just to give you a little bit of a flavor. So the first one, using this kind of combinatorial algebra, it looks like this. So there is a reduction that you can do here where you are basically computing inside a different ring, inside the Chow ring of the matroid fan. You need to compute alpha to the r minus k, beta to the k, where alpha looks like this, beta looks like this. Okay? Alpha is the sum of the flats containing I, beta is the sum of the flats not containing I, and this is the relations in the ring say that this is equal for every I. Okay? You're supposed to compute alpha to the r minus k, beta to the k, and get a number. Okay? How do you get a number? Well, a square free monomial is going to be 1 if you get a flag and 0 if not. So what you need to do is somehow say, okay, alpha is this, I need to raise to the r minus k, beta I need to raise to the k, and do some kind of magic so that in the end I just get, I figure out how many things are flags, how many are not. Okay. I'm saying that computing has a lot of freedom because for every one of these alphas, you get to choose an element of the ground set. And so there's a lot of freedom there, and you have to kind of think carefully how you should do it. You can do it lexicographically. This feels a lot like Grosvenor theory. And when you do it, you find that you get and this is essentially a reframing of the proof of the Alibracito Hall and Katz paper. What you get is a sum over the flags whose descent set is equal to k. So this is actually something that had arisen in Bjorn's proof of the topology of the order complex of the flats of a matroid. Something that Stanley had already done, and Stanley had already proved that the number of flags is equal to that. Okay? And this has to do with this theory of lexicographic shellings and so on. And in some way, if you've never seen lexicographic shellings, you kind of end up discovering it in this way. So, and I think this is an example of the kind of thing that, you know, you can try to do an geometric computation and then land with at some combinatorics that gets repeated. The second proof that I wanted to show you is if you proceed with these splines, okay? So you can write down what each one of these classes is as a spline. Alpha is T0 minus the T of the maximum, beta is T of the maximum minus T0, oh, minimum, sorry, minus T0. And the spline for the Matroid fan or Bergman fan, what you do is that in the chamber indexed by epsilon, you're basically recording what is the sigma minimum basis. Which for people who do Matroids, this is something really nice to see because we know a lot about this. Okay? And so, for example, you get something like this. You get that this is this. You multiply them and you get something that looks like this, and now you need to know what the degree is. So how do you compute the degree of something like that? Brion has a very beautiful formula that tells you, and this is a formula that's true for every fan. I find this very beautiful. What you're supposed to do is sum over the chambers of your fan. And each chamber, you're supposed to take the polynomial that you put here, this one, divided by the inequalities of the chamber. So T sigma 0 minus sigma 1 and so on. So for each one of these, you get a rational function, and then you're supposed to just sum this and magically get a number. It takes some work, but you can do it, and this is how you do this kind of computation. And like I said, this is written in that paper if you want to see it in detail. But this becomes basically a very careful combinatorial calculations with rational functions. With Minkowski weights, what you have to do is start with the Matroid fan, and then you basically can rephrase this as intersecting three fans: Matroid fan, the R minus K plane, and the K co-hyperplane. Okay, and so this fan displacement rule tells you you can intersect the Matroid fan, a small wiggle of this one, and a small wiggle of this one. And now you get to choose where you wiggle, and this ends up being a very useful thing. You can choose U and Vy until this computation is done more easily. Now you have to actually find those intersection points, and if you think about what that means, this is the kind of thing. Okay, so you have some fans, they're given by cones, and so you basically have to figure out when do cones intersect or not intersect, and you end up with these systems of linear equations and inequations. Okay. Again, everything is very combinatorially structured, so you can do this carefully, and you actually compute the intersection points, and you find that they're given by the right. So that's how you do a computation, right? Let me mention a fourth way of doing this coming from tropical intersection theory. I'll say this briefly, and this combines 2 points of view: the kind of spline point of view and the Minkowski weight point of view. And this is using some techniques developed by Allermann and Chow, where if you want to see how a piecewise linear function acts on a Minkowski weight, so the Minkowski weight is d-dimensional. When you try to multiply by a piecewise linear function, this turns into an action that turns d weights into d minus 1 weights. Okay, and basically, what this is that when you have a d weight around each d minus 1 ridge, there's something going around, and you have a function that is piecewise linear there, and this basically measures the nonlinearity. So there's some equation there that tells you the weight at that cone tells you how nonlinear the function is there. There's a formula, okay? So if you want to compute alpha to the r minus k beta to the k sigma m, you can do it one of these at a time, okay? And I believe this is actually what you did in his thesis. So you basically start with a Matroid fan, and then you have to say, okay, what happens when you act with alpha? You get some other Matroid fan. You find that alpha just kind of truncates the Matroid. Now, what happens with beta? Beta does some other thing, and you end up having to enlarge your family. You define these truncation fans that behave very nicely, and you basically are able to then compute. So this is another. I think I wrote it, but I didn't mention it. That Matt Larson wrote me last time that I gave this talk with a different proof that uses this connection where you have the dictionary between the Chow ring and the K ring, and you can use the Mullen-Polytope algebra to do a proof that ends up relying on some Earhart theory that Alex I think had done. And then I got an email from Katz last night telling me of another proof that he just wrote down. So yeah, there's a lot of ways that you can approach these kinds of computation. Okay? Let me just mention now some more recent results and so okay, I started with this one and I gave you a bunch of different proofs, and so here's another set of results that have improved in various ways. Okay. Let me just go down that list. So I'll start with this work of Lucia Lopez de Medrano, Felipe Rincon, and Chris Shaw. They introduced the CSM cycle of a Matroid. And this is a tropical analog of the CSM cycles from classical geometry. So this is like an analog of the Chern classes when your varieties are not smooth. And when you look at when you try to do the algebraic geometric computation of what is the CSM cycle of a hyperplane arrangement complement inside the wonderful compactification, you end up running into this object, which is the K skeleton of the Matroid fan with some intricate weights. So you get the Matroid fan, but you don't get the R-dimensional thing. You get the K-dimensional thing for each value of K, and in each facet, the weight is the product of beta of certain beta invariants. And they were able to show that the degrees of those are the coefficients of the chromatic polynomial evaluated at q+1. It's also known as the H vector of the Matroid. And for this result, as far as I know, there's two proofs. The first one was tropical geometric, and it's using some of these tools from tropical intersection theory and do push forward and pull back max of the way that I showed you to do some kind of deletion contraction argument, which is basically when you want to do things recursively in Matrix, this is what you do. Okay. Ashraf and Bergman soon after that found a different proof using the fan displacement rule. Okay. So they take these things and then intersect them with corresponding tropical hyperplane. And what I find interesting about that one is that when they do that, everything ends up reducing to this very beautiful work of Joan and Latvernias on basis activities. So that's one more recent development. So in joint work with Graham Denham and Simonyi Hall, we defined this conormal fan, which maybe I won't get into too many details at the moment, except to say that the support of the conormal fan is just the product of the Bergman fan of M and the Bergman fan of the dual matrix. Okay. I will explain why we needed a specific combinatorial structure on it, a specific fan structure. So this is what the conormal fan is. And we were able to show that these coefficients arise at the intersections of this kind of hyperplane class and a twisted hyperplane class. Okay. It was the main combinatorial result in our proof of the conjectures of Berlowski and Dawson that these numbers were log concave. Okay. So Daoji, with your question, this is what first comes to my mind is that our first proof basically had to say, okay, we are going to do this with combinatorial algebra, and so you need some fan structure where you're going to compute. And then we did a very careful computation of the lexicographic expression, which ends up needing some kind of new objects in Matroid theory. We define these biflats and biflats and things like this, and it all comes out of this computation. That was quite hard, and it develops some new combinatorics of matrix. Because, so if you look at my previous slide and this slide, we're talking about the same coefficients, and we also expected, I mean, this is all motivated from Lagrangian geometry, where in fact, one way of understanding CSM classes, this is due to Saba, is that you can go to the CSM classes of a variety, are the shadows of the characteristic cycles in the conormal bundle. And that gave us the idea that this was kind of like this is the topical version of the conormal bundle for Matroids. And so we wanted to prove some kind of statement like Saba's method, saying, okay, the shadow of these things should be the CSM classes. And so this statement is actually stronger than this one. The push forward of delta to the k in the conormal fan is equal to the CSM class of the Matroid and the Matroid. I think one thing that I want to say about this is that I think this is the computation that helped me appreciate that it was the push forward of Minkowski weights is quite subtle, and if somebody has more expertise than I on this, on how you push forward Minkowski weights in a systematic way, I would love to know. But here, I think it's striking that, I mean, these things are very simple, and the delta to the k is just the usual thing that looks like this. And when you push it forward, you get these CSM classes in the matrix. So there's a lot happening in that computation. But once we had that, then we could rely on the logarithmic shot to also give another proof. A more recent result. This is joint work with Chris Ure and Robert Penaguiao. This was a conjecture of Sturmfels coming from work on likelihood degenerations. This is coming from algebraic statistics. And maybe looking at the time now is not the moment to say too much about the context, except to say that they have this very concrete degree computation that they had in mind. So in this paper we have two proofs. One of them uses Minkowski weights, and maybe one thing that I want to say about this proof is that if you find yourself having to intercept Minkowski weights and things that are in the braid arrangement or some similar fan, we develop some techniques there that are useful. For example, this comes back in the recent work of Andy Burgett and Alex Fink on the resolution of Spire's conjecture. There's aspects of it that are how do you do fan displacement for subfans of the braid arrangement or other arrangements that are similar? So we do this here. We end up connecting to Ziegler's theory of beta and DC basis, and the other proof that we have, I find very. I mean, I find it very strange, but it works in some sense. This result is it looks very similar to this work of to a resultant the Bergman pink 10 paper. So we had the right-hand side was the same, the left-hand side looked similar. And what we found is that the left-hand side, when you subtract them, you don't get 0, but you do this thing where you can factor out some linear thing and get 0 to some gymnastics. So we end up using that kind of computation. And maybe I'll just conclude just with one word about this new work that we're doing with Van Dennen, Chris Uren, we are looking at the kind of augmented version of this story. And maybe I'll just put this result in front of you and ask you if you have seen enumerations of this sort. And I think with that, I will thank you for your attention.
Can I ask a silly, not very coherent question? So, so just about, so the, okay. So the general question is are there instances of like say lock and common inequalities where we have an understanding of like the equality cases non-numerically? The sort of motivation is that I guess in your joint work with June and Graham for Dawson and Brodsky, there is like another paper that came out around that time, like Bridget Smith-Henson, and there was this like funny lower bound with like the H vector thing, but it seemed a bit random. I was wondering if there are any instances if you understand what that means, sort of thing means. I don't know.
Mm-hmm. Let me say let me say a couple of things about that. One is that actually so there's two conjectures about H vectors, which one is about the H vector of the broken circuit complex, the other one is about the independent complex, and one ends up being like harder than the other one, but but as far as equality cases, I don't think that I have anything intelligent to say about equality cases. I mean, this is a notoriously hard question, and I don't think that's that I have some.
Yeah. We've talked a little bit about the bipyramidahedron. Is there like a characterization in terms of like edge directions or facet directions for that, or what's like the most concise way to think about
it? If you don't mind, let's talk about it one-on-one, because I think it might be more technical than
sure.
But it's definitely more intricate than the pyramidahedron. I'll say that. I'll tell you about it though.
I think I missed something on the D slide. There's a word can I come back? Yeah. So, why do you speak about structural critical points here? So.
Yeah. So okay. Let me. So in this paper of Agostini et al, they have this kind of the open question, which is find the tropical critical points of this algebraic statistics problem. And in some sense, actually, I'm glad you asked that question, because this is an example where they wanted to not only know the number of the degree of the intersection, but they actually wanted to know what are the intersection points, and that's what I'm calling tropical critical points. Is what are actually these points, because then they can lift them back up to do algebraic statistics computing. So tropical critical points, in that sense, it's actually finding this computation of the intersection of the Minkowski weights.
I guess you haven't explained the arboreal pairs very much, but how does that relate to the last slide where you're asking for these partitions into with independent sets?
It's okay. It's quite different. Maybe what I'll say is just that for every pair of partitions, we end up defining these trees, and then they form an arboreal pair. Some condition happens, and basically the combinatorics of partitions into playing are all in this computation. Which in this case it's a different kind of problem, where the idea is you have a ground set where you have two matrices on that ground set, and now the question is what are the ways of taking some set and expressing it as a union of an independent set in the first matrix and independent set in the second matrix. And these are the numbers that come out in that computation.
I think I was gonna ask a similar question, right? This result in principle should generalize the previous ones. Is that accurate?
In
principle,
not
like-
that I know at this moment.
Well, because like some of the previous ones are M1 and M2, where M2 is like M bar or M1 bar or M1 contract and edge, right? Am I misinterpreting that?
Let's talk about it some more, but there's also a distinction between whether you're doing the augmented case or not the augmented case. So this is, so in the previous case, that was the older Bergman fan, and these are the augmented Bergman.
I see. So they're slightly different.
They're related, but yeah.
I was thinking, this is what you're gonna say too.
Yeah,
Yeah, okay, then,
but okay, I was just gonna say that. I think there's also a difference in that, you know, I don't know this work yet, but probably here we have like a line bundle with like the linear, in the representational case, the linear space for M1 and the linear space for M2, whereas in the bipolynomial case, it's like a linear space and an inverse linear space.
Yeah.
Yeah, and I don't know quite how to square that difference yet.
Yeah.
I was gonna say, this is just your criterion for when do the variables appear in the defining equations for two variety.
The augmented version, right? You expect the augmented thing to like add a simplex, add a beta, and yeah.
I'll also say that there's more to be said yeah. I think we're in the process of making concrete some of these questions. I think we should probably stop because it's lunchtime and I don't want to keep you from your lunch.
To be continued at lunch.